As promised, I'm going to show you a strategy that you can use for questions 1 through 3 that may help you visualize this series in a helpful way, especially if you couldn't really think of any useful tools yourself. Even if you did think of a useful tool, and ordinarily I'd be thrilled if we could share as a class and talk about these useful strategies, I'll share with you a strategy that's actually become quite famous in the math world, and you can compare it to your own to see if there would have been any kind of overlap, or to see if maybe you were on the same track as a famous mathematician who's often accredited with a kind of groundbreaking approach to series. If you do want to go down a little mathematical rabbit hole, this might be a good name to Google, especially if you have some time and want to actually think about this a little bit. The name of the mathematician who's often associated with the arithmetic series is Gauss, G-A-U-S-S. Gauss was a mathematician in the early 1800s, but he actually started thinking and really kind of exploring the relationships between series of numbers as a small child. And there's a famous anecdote in the math world that relates his strategy for coming up with what at the time was a really difficult task. The story has certainly kind of varied over the years, and you can Google it and read for yourself all the different variations of this story, but it basically goes like this: that as a precocious child who was already kind of known for being at the top of his class, when he was 7, he apparently was being a bit annoying at school, as sometimes the precocious children are wont to do. And as the story goes, his teacher wanted to just kind of keep him occupied, to shut him up for a little while. So his teacher gave him what he thought would be a very time-consuming, tedious task. Carl, go to the corner of the room and add up all the numbers from 1 to 100. Figuring, this kid is 7 years old. This will take him a nice long time. I can finally catch my breath. I can get a bit of peace. The rest of the children can focus on something else for a second while the annoying kid is in the corner just adding up numbers for a while. The teacher thought he was oh so clever to come up with such a wonderful task for a 7-year-old. Well, again, as the story goes, in a matter of moments, Carl Gauss popped right back up and said, "Oh, I know the answer. The answer is 5,050. And, of course, the teacher, who in this day and age probably just came up with the problem off the top of his head. In the 1800s, it's not like he had a quick calculator or a computer that can verify that answer for him. The teacher was shocked. First of all, thought it was made up, and then thought, no, there's no way. How has he done this? And what eventually came to light in Gauss's writings and through some insights that he eventually shared about his own mathematical processes, the teacher realized that Gauss visualized the numbers from 1 to 100 in a really interesting way. And I'm going to show you his visualization in question number 1 first, and I'm going to let you kind of abstract how you think Gauss might have done it with the numbers from 1 to 100. What Gauss pictured when he pictured those numbers is almost like a long ribbon of numbers. So picture the numbers from 1 to 10 as a bit of a ribbon being just like a long flat thing. Now, as you know, with ribbons can kind of fold back on themselves. So ribbons are pliable and manipulated very easily. And the reason why I'm mentioning that, and again, to just kind of picture a ribbon, so to speak, think of something that looks like this. A ribbon can easily bend. A ribbon can easily be manipulated and twisted in all different ways. Picture this ribbon of numbers from 1 to 10. What Gauss pictured is a ribbon of numbers, 1, 2, 3, 4, 5, but then he pictured the numbers bending back on themselves. 6, 7, 8, 9, and 10. So see that ribbon kind of take shape? He pictured from 1 to 5 and then bending back on itself 6 to 10. Now the reason why that's kind of helpful is because when you look at each pair of numbers that seems to line itself up, when you bend the numbers back on themselves, each pair of numbers has a relationship. 1 and 10 adds up to 11. So do 2 and 9. So do 3 and 8. So do 4 and 7. So do 5 and 6. So if you think about this little ribbon effect, Each pair of numbers in the ribbon adds up to 11. And if we have 1, 2, 3, 4, 5 pairs of numbers, 5 11s adds up to 55. Now check your answer to number 1, letter A. If you added up all the numbers in whatever strategy you devised, you probably got that the sum was 55. But think about that ribbon. Think about how bending the series of numbers back on itself and thinking about pairs could help you with more tedious tasks like question number 2. Picture the ribbon of numbers that would go from 1 to 20. If you visualize that ribbon, you don't necessarily have to write it all out, but maybe just writing out a few terms would help. You'd probably want to bend the ribbon at the halfway point, so adding up to 10, and then bending back on itself from 11, 12, 13, 14, 15, 16, and then kind of thinking all the way to the end of the ribbon like so. Kind of cheating it a little bit, but hopefully you can see where I'm going with this. I'm not necessarily going to write every number, but picture the ribbon again. All the numbers from 1 to 10, and then all of the latter half of the series from 11 to 20 in that second row. Again, notice what you get. You get a pair of numbers partnered up, so to speak, that add up to 21. And then another pair of numbers that adds up to 21, and another pair of numbers that adds up to 21, and another pair of numbers that adds up to 21, and every pair of numbers would add up to 21. So if every pair of numbers adds up to 21, and if you figure you have 1, 2, 3, 4, all the way to 10, that must be 10 pairs of numbers. 10 times 21 would be 210. And if you did actually add up all of the numbers and get 210 for this problem, then obviously you were correct, but maybe thinking of it in this more visual ribbon pattern could have given you a more efficient way, especially if you took quite a bit of time to figure out that the sum was 210 when you did that question on your own. So if you haven't yet, try to adapt this strategy to question number 3. And if needed, ask yourself, how could I actually make this more doable? First of all, how could I predict where the bend is going to occur? Do I even need to draw out all the numbers? Do I need a diagram? Could I just quickly figure this out? And see if you can come up with some sort of strategy that makes sense for what you did. Now, if you have some time between now and the next video, try Gauss's problem. Remember Gauss's 7-year-old problem that he had to find the sum of the integers from 1 to 100? Try that. See if you can try this little ribbon strategy, this bending the numbers backwards strategy, to do what Gauss did. Now remember, Gauss was 7 and didn't have a calculator. He was doing this in probably the late 1700s as a small child, but he was pretty precocious. So if you feel like you need a calculator to do the calculation, it's not the end of the world. We can't all be Gauss. But challenge yourself. If you can visualize the numbers, can you think of a way that you can do it without a calculator or with very minimal scratch work? And see what you can do to channel your inner Gauss. Between now and the next video, try to finish question number 2 and question number 3, and try the extra little Gauss challenge, the numbers from 1 to 100, and see if you can make sense of that bending strategy, that ribbon strategy I call it. In the next video, we'll talk about how to adapt the ribbon strategy and how to generalize the ribbon strategy for all sorts of additional problems so that you don't have to rely on long, tedious calculations or very inefficient ways of adding and adding and adding that would genuinely just take too long.